All right, so we've been talking about work and how much work you do on an object. And the definition of work was the amount of energy that is expended to displace an object. And I made sure to point out the word energy in that. So energy here, where we're going now, is conservation of energy, meaning conservation. Energy is not created or destroyed, but we're going to get to that. Energy is the ability to do work. So there's this relationship between energy and work. If you have energy, you can actually do work. And that's kind of the physics definition. The concept of energy is a somewhat nebulous concept, right? Of its power, its strength, so to speak, not physics terms, power, but power, its strength, its, if you're energetic, you can do a lot of things, aka you can do work, right? Now, conservation of energy. Energy cannot be created or destroyed. In other words, it's only transferred. It goes from one location to another location. Energy doesn't magically occur or magically disappear. It only is transferred from one type of energy to another type of energy, or from one object to another object. Now, two basic types of energy. Kinetic energy, and there's lots of others, but kinetic energy, which is the energy of motion, and potential energy. Now, potential energy actually can be divided into a lot of different forms. Spring potential energy, because whenever you displace a spring, whenever you, let's say you're crunching, let's say whenever you crunch the spring with an object on it, it has energy stored in it. And the way you know that is whenever you release the spring with the object on it, it shoots the object off, it does work on the object, causes it, and propels it forward. That's how most older, before air-powered there, that's how spring-powered BB guns work. It shoots the BB, right? It does work on that BB, so there's spring potential energy. There's chemical potential energy. There's all different places that energy can be stored. Here in this unit, the main one we're going to look at least here in the beginning, is gravitational potential energy. Okay? Now, gravitational potential energy just means that you are above the Earth's surface some distance, or really it's above the Earth's core, but the surface is going to stop you. So you are above the Earth's surface. It's energy stored by an object moving away in a force field, and for gravitational potential energy, it means that it's the amount of energy stored because you are upwards in the force field, in the gravity force field, and gravity wants to pull you back down. Gravity will do work on you to pull you back down to the surface of the Earth. So here's a quick little demo with just kinetic energy and gravitational potential energy. Just a little picture. I have a nice little U-shaped hill here, a half pipe if you will, and a ball in that. And at the very top, some height h, this ball, whenever released, has all potential energy, if you're just releasing it, all gravitational potential energy. And as it rolls down to the very bottom here, you have all kinetic energy. And during this time, energy is being transferred from gravitational potential energy into kinetic energy, or the energy of motion. Down here at the bottom, it's no height above the surface, so there is no potential energy. It's all now kinetic. It's moving at some velocity, some speed there. And then as you coast, if you will, back up the hill, slowing down the entire time, you're transferring your kinetic energy back into potential energy till at the very top. Now it's all potential energy. You pause for that literal instant, right? And then you would turn around, transferring back from potential into kinetic, so on and so forth. In this part of the unit, we are not going to deal with friction. Friction is the great stealer of energy. We need another small add-on, which will be the next video, to deal with friction there, because friction is going to cause energy to be stolen. It's not technically lost, it's just transferred. Friction transfers energy into heat. Let me give you the equations here for this. Kinetic energy, Ke, is 1/2 mv squared. 1/2 times the mass of the object times the velocity the object's going at squared. Gravitational potential energy is found in mgh, mass times the acceleration of gravity, 9.81, times the height above the surface. Now, if you were looking back at other videos, and I made sure to emphasize this, I said, hey, take note in this work problem, whenever we're lifting something straight up, the amount of work that needs to be done ended up coming out to be mgh. here it is, circling back around. Potential energy is mgh, which should set you up for this next video of work energy theorem. Now, this conservation of energy idea, what that means is the total energy in a given system before an event is the same as the total energy after an event in the exact same system, or after a little bit of time passes. So what that means is I can write, the total energy is going to be all the kinetic energy plus all the potential energy. I can write kinetic energy initial, so I'll use KEI, plus the potential energy initial, right, equals the kinetic energy after, or after some time passes, plus the potential energy initial. So in our ball rolling up and down a hill that I kind of moved off to the side to give myself enough space, if I chose the initial point to be at the very top of the hill, right, and then the final point to be at the very bottom of the hill, I could say at the top of the hill, there is no kinetic energy, so this could completely go away, right? No initial kinetic energy, it's all potential energy, which I'm going to get from this equation here, right? And in the final, if I choose the very bottom of the hill, at the very bottom, there is no potential energy. We are no height above the Earth, so PE would completely go away, only leaving me with kinetic energy final, which I get from this equation there. So if I wanted to break it down a little bit further, I could do 1/2 mVI squared plus mghi equals 1/2 mvf squared plus mghf. As, if you will, a not final, but if all you're having is gravitational potential energy included in this kind of equation for you that you could use. But understand, this is not the conservation of energy equation. There is no given equation, all right? There's all different types of energy: spring, chemical, gravitational, thermal. There's all sorts of types of energy that could be converted between the two. The conservation of energy equation, if you will, is just the total energy initial equals the total energy final, and you've got to then plug in what each of those energies are, initial and final, and set them equal to each other. Now the unit for energy, which I neglected to give at the very beginning, and I should have, the unit for energy is the same as the unit for work. It is the joule, okay? It's the capital J joule there. It's a scalar function. It's not a vector, just like work. All right, so a somewhat simplistic problem. A car rolling down a 32-meter high hill. How fast is it going to be going? 1/3, 2/3, and at the bottom of the hill. Now, the nice part about energy is it's a scalar. I didn't put that in the last slide, and I should have. Energy is a scalar, not a vector. Direction doesn't matter. Just like work, it's a scalar. Direction doesn't matter. So here's a problem. A car rolling down the hill. How fast is it going to be going at these points? Without conservation of energy, this problem could actually get very difficult. I would need to know the average angle of the hill, right? I would work Newton's second law there. If we're neglecting friction in this one, I'd need to work Newton's second law to figure out the force coming down the hill, right? And then I would, from that, get the acceleration. And then I would have the hypotenuse, the different hypotenuses of the triangle as my displacement, and then work a kinematic equation. That's 3 separate steps there that I would need to do. Or 2 separate steps there that I would need to do to get that. Conservation of energy, you don't have to worry about it. I'm going to solve first for how fast it's going to be going 1/3 of the way down. So energy initial equals energy final. At the very beginning, at the top of the hill, the only thing we have is potential energy. So I'm just going to write the potential energy equation. mghi equals. Now, 1/3 of the way down, I have two types of energy. The car has picked up speed, so now I have some kinetic energy. 1/2 mvf squared, but I'm not all the way down at what I choose my 0 point to be. By the way, that's another nice thing about conservation of energy. Really, with any physics problem, you can choose your reference point. So with conservation of energy, you would choose your reference point 0 to be something that's easy, and pretty much with gravity, it's always choose the ground as your 0, okay? So it hasn't gotten to the ground yet. It hadn't gotten down to 0, so I do have some potential energy left, mgh f. So now I'm going to substitute in some numbers here, m times 9.81 h 32 equals 1/2 m VF is what I'm looking for. That's my goal. How fast is it going to be going? Plus mg times 9.81 times my final height, 21.3 meters. By the way, here's how I got that. 1/3 of the way down means that the car has gone 1/3 of the distance to the ground, right? So there's 2/3 left down here and 1/3 left up there. And so you just take 32 times 1/3, right? That'll give this distance. Then you're going to need to do 32 minus that, right, to see how high it is above the ground relative. If you'd like, aka times 2/3, 32 times 2/3, give you 21.3 meters above the ground. And now it's just a little bit of algebra. But before I do that, let me point out something to you. I don't know mass of the car, but it's not needed if I don't have friction. Notice mass is in all of my terms. It's here, it's in this term, and it's in that term, so I can cancel my masses out, divide both sides by m, masses go away, leaving me with just my straight algebra problem here, 1/2 VF squared plus 9.81, 21.3. So now we subtract this guy to the other side. And putting those together gives me 104.97. Now I'm going to need to multiply both sides by 2 to cancel out that 1/2 here. So whenever I multiply both sides by 2, those cancel. So now I got 2 times 104.97. And then equals VF squared. And then to get rid of the square, I square root both sides. So my final velocity is going to equal the square root of 2, whatever 2 times 104.97 is. And with significant figures, it was 14.489, but with significant figures, that's 14 meters per second squared because it only gave you 2 significant figures, 32 meters high hill. If you had rounded a little bit differently somewhere else, maybe in the height here, because this was technically 21.333, maybe that would have pushed that up to 15. All right, so now let's do the 2/3 and at the very bottom. All right, so I have the exact same thing for at 2/3 of the way down. Total energy is initial is equal to energy final. In the very beginning, it's all potential. The car is not moving, we're assuming, at the very top of the hill, equals my final velocity, my final kinetic energy, plus my final potential energy here. So I can cancel out my m's. I already know that, right? So let's go ahead and let's get rid of them. Let's substitute in everything that we know. All right, 2/3 of the way down is 10.7 meters. Flip back to the other slide to look at the picture of that 32 meters high after you go 2/3 of the way down. So you're multiplying by 2/3 and subtracting from 32, right, to get it relative to the ground, gives you 10.7 or 10.666 meters. So at 2/3 of the way down, I come out with 20 meters per second as the final velocity there. Now, at the very bottom over here, my initial total energy has to equal my final total energy. At the bottom, my initial is all gravitational potential, mgh, and at the very bottom, it's all kinetic, 1/2 mv final squared. There is no potential left over because we're at the very bottom. All right, so once again, I can cancel out my masses. Notice there's a mass in each term here. And with conservation of energy, if you're dealing with normal kinetic energy, 1/2 mv squared, and gravitational potential energy, mgh, and that's it, and you don't have any friction involved, masses pretty much always cancel there. So this leaves me with just plugging in numbers and solving the algebra. And whenever I'm all done, I come out with 25 meters per second if we're rolling all the way down to the bottom of the hill, 32-meter high hill, and there is no friction.